In part 3 of the tutorial, we will discuss security in the context of distributed optimization and machine learning. In the first two parts, we talked about some examples of such algorithms without worrying about security or privacy. So we have seen some basic algorithms that are designed for the server-based architecture as well as decentralized or peer-to-peer architecture. And the question that we want to address today is what would happen if some of the agents that are participating in this distributed computation are compromised or adversarial or faulty. Essentially, they may be misbehaving for a variety of reasons. And the question becomes then is how do you perform this distributed computation or distributed optimization or distributed learning if some of the agents inject bogus information? So for instance, in the algorithm we saw previously, in one of the algorithms we saw previously, the agents are supposed to upload the gradients of their own local cost functions to the server at the current estimate xk of the optimal value. However, the faulty agents or the compromised agents may potentially provide a wrong value to the server. So for example, this value may be incorrect because agent number 3 in this example may be compromised. And then if the server were to apply the standard gradient descent step, then it will perform incorrect computation. And so the question is, how do we tolerate such faulty agents? And what do we even mean by faulty agents? So for that, we are going to use something called the Byzantine fault model, which was introduced in the context of distributed computing in the 1980s. And the essential concept here is that under the Byzantine fault model, we will not try to impose any limits on the bad behavior of the faulty agents. So the faulty agents can behave any arbitrary way, and the algorithm has to be able to tolerate any arbitrary behavior from a certain number of faulty agents in the system. This is a model that we are going to use. In practical system, the behavior may not be entirely arbitrary, depends on the kind of adversarial agents we have. If it is in fact a fault, such as failure in the communication channel or maybe the memory faults on a computer, then those faults are somehow often limited in their manifestation, and therefore the behavior of the faulty agent may also be limited. On the other hand, if the faulty agents are actually compromised entities, then the behavior may in fact be quite arbitrary. So the model that we are using allows essentially any behavior at all from the faulty agents. In fact, we will allow the faulty agents to cooperate with each other for free, meaning even without talking to each other, they can learn about each other. And so we give a lot of power to the faulty agents here. Now, when you have such faulty agents, they may misbehave in a way to tamper the outcome of the computation that we are trying to perform. In this case, the distributed optimization algorithm. Recall that we are trying to solve this problem, meaning we have a number of agents, let's say n agents. Each of the agents has a cost function. Agent I has a cost function fi of x, where x is the argument. And what we're trying to do is to compute the argument that minimizes the aggregate cost function over all the agents. And we saw examples of this last time. And this was one of the examples we saw, the so-called rendezvous problem or the problem of meeting somewhere, the consensus problem. And if you recall, in this setting, in this example, we have 3 agents, and agent I has cost function fi of x. They need to pick a location x where the total cost over all the agents is minimized. And we saw the examples of algorithms that can actually solve this problem. But now we are going to allow some of the agents to be faulty or compromised. And in particular, we are going to assume in this example that agent 3 is compromised. Now, what the agent 3 can do is to behave in a way so as to bias the outcome of the computation. So for example, if I were to be this faulty agent number 3, what I could pretend is that the cost function I have is such that the cost of meeting where I want to meet, perhaps I want to meet exactly where I'm right now, the cost of meeting at my current location is very low. In fact, it's zero for me, and it's extremely high everywhere for me, right? So I could pick a cost function that has a zero cost here and then extremely high cost everywhere else. Now, if agents 1 and 2 choose reasonable cost functions, meaning cost functions that reflect their true cost, then when you minimize the summation of these three costs, because F1, F3x has been tampered, has been chosen adversarially, the agent 3 can ensure that the argmin of F1 plus F2 plus F3x is essentially the point where agent 3 wants to go. So long story short, by choosing a suitably tampered cost function, agent 3 can bias the outcome of the computation, in this case, distributed optimization, in arbitrary ways. And obviously, that's not desirable. Similarly, in the context of machine learning, which is perhaps of more practical interest, so in this example, we have 4 agents where the data is distributed at those 4 agents. And the goal is to minimize the global loss over all the 4 agents put together. And Fix is the loss over the data at agent I. Now, if agent number 2 is compromised, then it can potentially provide incorrect information, incorrect gradients during the distributed computation, so as to bias the distributed learning outcome to pick parameters that agent 2 wants to pick, right? So if he can adversarially affect the outcome of this computation in the context of machine learning. Now, this is obviously not desirable, and you want to somehow prevent a faulty agent from influencing the computation in an undue manner. And that's what brings us to this particular part in the tutorial, where the focus is on secure optimization and machine learning. I actually prefer the term fault tolerant. This is a matter of jargon. Some people call this secure optimization. Like I said, I prefer fault tolerance. That's because of my own background. And so I will use the term fault tolerance actually in this talk. So I have been working along with my students on this particular problem since 2015 now. And so some of the work I'm presenting today, in fact, comes from my own group. And of course, we will discuss work from other research groups as well. And so this discussion on fault tolerance will be divided into 2 parts. The first, I'll give you some basic results, and then we will discuss some specific algorithms for distributed optimization in the presence of adversarial agents. So before we can implement or design a fault-tolerant optimization algorithm, the first question we have to answer is, what are we trying to do here? So what is the objective that we want to achieve when there are compromised agents in the system? There could be one agent or more than one. And here is a reasonable objective that we are going to start with. Perhaps what we want to do is to ignore the faulty agents, ignore the compromised agents, and minimize the global cost over just the good agents. Remember that my initial objective was to minimize the summation or compute the argument for the summation of costs over all the end agents in the system. I have now changed that goal, and now I'm going to focus on just the good agents. I only care to minimize the cost, the aggregate cost over just the good agents. And this is a reasonable objective because the fault agents can behave arbitrarily. I cannot really take into account their cost functions. And this is perhaps the best I can try to do. And so this is what I mean. So we want to minimize the cost, the aggregate cost over just the good guys, the good agents in the system. Now, of course, the big problem is that we don't necessarily know which agents are good and which agents are faulty. And yet this is a reasonable goal to try to achieve. The question, of course, is can you in fact achieve this goal? And that's what we're going to talk about today. So coming back to the example of this rendezvous problem where 3 people are trying to meet. Now, this new goal that we have requires that we minimize or compute the argument that minimizes the cost over just the good guys. So therefore, you want to ignore agent 3 because in this particular example, agent 3 is faulty. And you want to minimize then the cost of agent 1 plus cost of agent, this should be agent 2, F1 plus F2 of X. And you want to compute the location X and minimize as a sum of F1X and F2X. This is the goal. Similarly, in the machine learning example, we had 4 agents, and let's say agent 2 is faulty. Then you want to compute the x, the argument x that minimizes the sum f1x plus f3x plus f4x. F2x is not included because 2 is faulty. Again, we want to achieve this objective without knowing explicitly that agent 2 is faulty. So somehow we have to get rid of the bad influence of the faulty agent. So like I asked earlier, is this really achievable? And the answer is that sometimes it is achievable and sometimes it's not. And there's a whole spectrum of problems that exist. And depending on which end of the spectrum or where on the spectrum we are in a given problem instance, that decides the answer. So for example, if we're at this extreme, where the functions are independent, and I will say a little bit more about what I mean by that, but if the functions are independent, then in fact, this objective is not achievable. And we will show, in fact, today very quickly that is the case. However, if there is a lot of redundancy, or if there is enough redundancy in your data or in the functions, the cost functions of different agents, then in fact, we can solve this problem, meaning we can in fact compute the argmin of the global cost, rather the summation of the cost over just the good agents, if there is enough redundancy. And then we will discuss today what we mean by enough redundancy. So let's proceed. We will take examples at both the extremes. So let's start first with the case of independent functions, or in other words, there is no redundancy in my system. And then we will talk about function with redundancy, and we will take 2 specific examples of functions with redundancy, where in one instance we'll try to achieve what I call exact resilience. In the other case, we'll try to achieve approximate resilience. So we are going to begin with independent functions where there is no redundancy. And here's an example to show that if the functions are independent, then we in fact cannot solve the problem. So what do I really mean by independent? I'm not going to try to define this formally, but intuitively, all we mean is that knowing the functions, the cost functions of some of the agents, we cannot infer anything about the cost functions of other agents in the system. And that's the notion of independence here, that the information I know about some agents tells me nothing about the other agents. And if such independence doesn't exist, and the functions are somehow dependent or correlated, then you can exploit that dependence to solve the problem. But here is an example. Suppose the functions are independent, and there are 3 agents in the systems. Let's call them A, B, and C. And they're in fact standing on a street at locations A, B, and C as well. So we're calling the locations and their agents the same name. And now the goal is for these agents to meet somewhere on this street. So it's a one-dimensional problem. The argument is a scalar. And the goal is to meet at one point on this street, and to pick a point that minimizes the total cost, except that now we have a bad agent, namely agent C. Of course, agents A and B do not know that agent C is faulty. They cannot just look at the cost function and decide that agent C is faulty. There is no a priori information available to infer who is faulty. But agents A and B have to allow for the possibility that there is one faulty agent, right? So we are going to try to design an algorithm that can tolerate one faulty agent. So what would that mean? Let's think about this from the perspective of agent A. If I am agent A, and of course I don't know whether agent B is faulty or agent C is faulty, or if either one of them is faulty, but I have to allow for one of them to be faulty. Now, if I allow for the possibility that agent C is faulty, then my objective of minimizing the cost over just the good guys will say that I must minimize f1x plus f2x. These 2 functions, the sum of these 2 functions is what I try to minimize. And if you try to do that, then the argmin will end up being somewhere here, closer to node A in this case. On the other hand, if I'm agent A, I have to also allow for the possibility that perhaps agent B is the bad guy, the bad agent, and agent C is in fact fault-free. Remember that I'm trying to tolerate one bad agent. If that's the case, then I have to ignore the cost function of agent B, and minimize the sum of cost function A and cost function C, and that would be minimized somewhere at this point as shown. Now, we saw earlier that if agent C were to be faulty, I have to minimize at this point on the left. If agent B is faulty, I have to minimize here at the point on the right-hand side. And obviously, I cannot choose one or the other without knowing who is faulty. And like I said earlier, we don't actually know who is faulty just by looking at the cost function. So we don't have any information that tells us anything about who is faulty, and yet we want to solve the problem we posed, which is to compute the argmin of the cost summation of the cost function over just a good agent. And this example shows that because we do not know who is faulty, and the functions of some of the agents don't tell us about anything about the functions of the other agents, the functions are independent, we cannot actually solve the problem. We cannot compute correctly in every instance an output that is the argmin of the summation of the cost function over just the good agents. So that's impossible. So it's a very simple example which proves that this problem that we set out to solve is in general impossible to solve. And then the question, of course, is twofold. One is, when is it possible to solve this particular problem as specified? And in cases where the problem is actually impossible to solve, what should we do? We cannot declare defeat, right? I mean, you suppose want to train a machine or meet for dinner, we still need to compute an output. And if the functions happen to be independent, or the dependence is not sufficient, and I have not defined what sufficient means, nevertheless, in all cases, I must solve the problem, I must produce an output. And the question is, how do I decide which output to compute, given that this problem itself is not solvable? Okay, so we're going to talk about these various questions, either the rest of the, during the talk today, or maybe in part number 4. So in particular, we are going to talk about different ways of approximating this goal. If this goal cannot be satisfied, then perhaps we can do something weaker than that, because we do not have the right kind of redundancy in the cost functions of these agents. And we'll discuss at least a couple of different ways of approximating this in some detail. And there are maybe more than 2 ways of approximating the desired goal. So here's the first one we'll talk about. And we're going to assume for now the functions are independent. Which is to say, there is no redundancy, okay? And without having defined what redundancy means formally, let's just rely on our intuition to sort of imagine what no redundancy means. Now, our goal was to compute this, the argument, the parameter x that minimizes the summation of cost function over all the good agents, just the good agents. We want to ignore the bad agents somehow. Now, this argument on the left is actually identical to the argument on the right-hand side, because all I have done is to multiply each of these functions by 1 over g, the size of set g. I multiplied each function just by a constant. Now, if you scale each function by a constant, it doesn't really change the argument that minimizes the cost, and therefore these two are actually just identical. So I've not really done anything interesting here, except that this is an interesting way to think about what we are doing. So if you think about the cost function here in this, on the right-hand side, it's actually a weighted sum of the cost functions for all nodes in set G. It's a weighted sum of all the cost functions that I care about, the cost functions of agents in set G. And it's not just any weighted sum, it's a uniformly weighted sum, meaning that all these weights are identical. One way to think about, interpret what we're saying is that there are a bunch of good agents, each of them has a cost function, and I care about them equally, right? So I want to give each of them the same level of importance, let's say, and therefore the same weight when I compute my output. So when I compute the aggregate cost, I care about all the cost functions in the set G equally, and therefore I want to assign them equal weights. Now, what I just told you in my previous slide here, that you can't actually solve this problem exactly as we set it out to be. To put it differently, I cannot compute this. At least I cannot guarantee that my output of any algorithm will be equal to this. So then the question is, can we do something different? If the ideal goal of uniform weights is not achievable, perhaps I can produce an output such that the weights of these different functions in set G are non-uniform. If uniform is not possible, is non-uniform somehow possible? Right? That's what I mean by unequal weights. And yet, we still want to unequal weights to I belongs to G. Okay, with the faulty nodes or the faulty agents, we don't want their cost functions to affect the outcome at all, which is to say that the faulty agents get the weight of 0, which is why those functions don't show up in the summation at all. So that I don't want to relax. I don't want the faulty agents to have any influence at all on my outcome, right? At least the outcome should look as if the faulty agents don't have any influence. And yet I want to try to achieve either the ideal goal or something close to that. So before we look at a solution and before I give you some results, let's get back to the example of the algorithm, the server-based algorithm we have seen before in the previous part of the tutorial. If you recall, in this server-based setting, the server keeps track of an estimate of the output. We are calling it xk. Initial, the estimate is x of 0, then it becomes x1, and each iteration looks something like this, where the server sends the current estimate to all the agents. Agents are supposed to compute the gradients of their own cost function and send them back to the server. For example, agent number 1 will send gradient of function f1 at xk back to the server. And once server has all these gradients, it can add them up and then take this particular step to compute the new value, which is called xk plus 1. And this repeats. And as we have seen last time, as k goes to infinity or as k gets larger, xk will approach the true minimum of the summation of the cost functions. Except that in this case, now we have a faulty agent. And it's not going to provide the true gradient of its cost function, or at least not the gradient of its true cost function. It can just make up a gradient or make up a cost function and provide the gradient of that. Any which way, the bad agent can provide bad information. And if we just apply the algorithm as it is, then this bad gradient is being included here in this summation. And therefore, the step that the server takes will be incorrect. It will not solve the problem. Neither the original problem, where we want to compute the minimum of cost of all the good cost functions. And given that just adding up the gradients is not a good idea, what should the server do? The intuitive solution is to say, let's not just add all the gradients, let's throw out the bad gradients, meaning let's throw out the gradient coming from agent 3, except that the server doesn't know that agent 3 is the bad agent. Just looking at the gradients, the server may not be able to tell which agent is faulty, if any, actually. And so you have to apply some filter, some way of cleaning up the data, in this case, the gradients, without actually identifying explicitly the bad agents. And here is a simple algorithm. As far as I know, this is the first algorithm that uses gradient filter or a fault-tolerant gradient aggregation for the purpose of solving the fault-tolerant optimization problem. This is the work of one of my own former students from 2015. And the algorithm is very simple. It only applies to the case where, at least the way it is written on this slide, it applies to the case where the argument x is a scalar. And we have the steps, lambda k. This is the size of the step we take. The step size is assumed to have some properties. These are fairly standard assumption, particularly for the step size in distributed optimization algorithms. Now, what I'm describing in the rest of the slide is actually how the filtering happens. Again, remember that the parameter for this particular example is a scalar. So those gradients are just real numbers. And the server is receiving the n real numbers, n gradients from the n agents. Some of them are faulty. And we are going to assume that up to t agents, out of n are faulty, okay, faulty or compromised. And so what the agent does to collect those ingredients, sort them, they're just real numbers now, throw away the smallest t values, the outliers, and the largest t values. And then compute the average of the remaining n minus 2t gradients. And what you get at the end of this is the so-called filter gradient. And then we're going to take the step as shown here. So the filter gradient goes into here instead of just the summation of the raw values of the gradients received from the agents. And we take a step in that direction. Now, later, either in this part or most likely in part 4, what we will look at are other filters that can be applied to the gradients, not just for scalar gradients, but also for vector gradients that have different behaviors and achieve slightly different properties. But in effect, all of them are designed to try to solve this problem correctly. I'm going to put correctly in double quotes because what correctness means itself varies from one paper to the next in this particular area. But the goal is to design or develop new ways of filtering the gradients to achieve some desirable properties on the outcome of the fault or an optimization problem. So like I said, as far as at least I know, this is the first such filter on the gradients. And since then, there have been many proposals proposing a variety of filters for the gradients. Other than that, the structure of the algorithm remains pretty much what I showed you on the last slide. The key distinction is in the filter design and the assumptions that might be made on the functions themselves, meaning the cost functions of individual agents. Different papers in this literature may make somewhat different assumptions about this cost function. And I will talk about that too in the next lecture or two. So what does the filter I just showed you achieve for the scalar case? Recall that our goal was to compute the argmin of the summation of cost functions of just the good agents, preferably with uniform weight, identical weight for all the good agents. And I said we can't actually achieve that when the functions are independent. And in fact, this algorithm I showed you doesn't achieve that when the functions are independent. So what can happen, in fact, is that not only do the bad agents get weight of 0, that's desirable, right? We want to get rid of the bad agents. So we do assign the weight of 0 to the bad agents. That does happen. The way we filter those gradients, it has that effect. However, it has also the downside that T of the good agents may also get the weight of 0. What does that mean? If we are trying to meet for dinner, let's say there is 10 of us, and let's say T equal to 2, meaning I want to tolerate 2 bad guys, then the final outcome of my computation, I wanted to rely on those 8 good cost functions alone. I want to pick a location such that the cost is minimized for those 8 agents, the good agents. And that will mean the weight assigned to the bad agents is 0. So that's the desirable part. But this says that the undesirable part is that it's possible that 2 of the good agents also get the weight of 0, which is to say that when we pick the place for dinner, out of these 8 good guys, we might actually end up ignoring the opinions of 2 good agents and only pick an outcome, a location that depends on the cost functions of 6 good agents. That may happen. And that's the cost of tolerating bad agents, T bad agents. Secondly, given that T good agents potentially have weight 0, and T agents may be potentially bad, that leaves n minus 2 T agents. If the weight was to be assigned uniformly to all of them, then they should all get the weight of n minus 2T. We are not able to match that 1 over n minus 2T exactly, but one can come quite close to it within a factor of 2. So here is what is actually achievable. The algorithm that we just showed, let me go back for a second there. This is the algorithm, right? We take this step as usual, except that the gradient here, what we're using here is not the summation of the gradient of all the agents, but the filter gradient, which is obtained this way, where the server collects the n gradients, throws out the smallest t values, the largest t values. This is for the case where the argument is a scalar, and therefore the gradient is a scalar. And the filter gradient is simply the average of the remaining n minus 2t gradients. That's the algorithm I'm talking about. And this is what this algorithm achieves. The output it produces, as k goes to infinity, the output will converge to a value. The argument will converge to a value. That's an argument, the argument that minimizes a weighted cost function, weighted cost of just the good agents, where the ith good agent gets the weight of alpha I. Now, the property that the alpha I has is the following, that at least n minus 2t of those good agents will each have a weight of at least 1 over n minus 2t times half. So it's not quite uniform, but within a factor of 2 of uniform weight. And like I said earlier, we might compromise t, rather we might sacrifice t good agents in the sense of giving them the weight of 0. And we get this guarantees that the bad agents surely have a weight of 0 in this outcome. So this is not perfect because it's some of the good agents are being ignored, but you can also prove that no other algorithm can do better, meaning no algorithm can guarantee that less than t good agents are sacrificed. So there is always no matter what algorithm you design, you may have to set, depending on the cost functions you have and depending on how the faulty agents behave, t good agents may be sacrificed. No algorithm can avoid that. And so in some sense, this particular result is optimal in terms of how many good agents get non-zero weights. Like I said earlier, the bad agents do get a weight of 0, and that's quite desirable. Now, this particular algorithm has, or if you try to extend this kind of algorithm to arguments that are higher dimensional, let's say dimension d, then what you end up with is the situation where when you want to tolerate t false, let's say t equal to 1 or t equal to 2, the number of agents and good agents I'm sacrificing scales not only with the number of false t, but also the dimension of the argument x, let's call it d. In particular, you may lose so many d times t agents, good agents. You may lose them in the sense that my outcome may assign them the weight of 0. And that's not a very nice property because this dimension d may actually be very large depending on what problems you're dealing with. Let's say in machine learning, the dimension is actually the length of the parameter vector, and that could be in millions, right? And so this does sound like this is not a very good outcome. I should point out, actually, before I proceed here, going back, even though what we're really producing is some output, let's call it x hat, that is the argument that minimizes a weighted cost over all the good guys, with weights having this property. What the algorithm produces is actually this x hat, the argument. The algorithm does not tell you what these weights are. So those weights are not actually explicitly computed. All I'm saying is that those weights have this property provably, even though we may not actually know what the weights are. Coming back to this idea that we might compromise DT agents, good agents, if D is large, this is obviously not desirable. As I said, in the machine learning setting, D can, in fact, the dimension can be very large. However, what saves us in the case of machine learning is that, in fact, those functions are not usually independent. To put it differently, if many agents are collaborating in the distributed learning problem, then the loss function, the cost function of each agent I is the loss over the data that agent I has, and the data that agent 1 has and the data that agent 2 has, and so on, that may not be independent. In general, it is actually not independent. It's quite correlated. And so in some, those cost functions are usually not independent, and therefore you can exploit the dependence to circumvent this particular problem in many domains. However, when the functions are truly independent, we are stuck with this negative result. And again, we cannot really improve on this worst case result. But luckily, the functions tend to have some redundancy or correlation, and we can exploit that, as I will illustrate later. In the machine learning setting, I already said some of this, so maybe I'll go through it quickly. What we wanted to do was this, right? Minimize summation f1 plus f3 plus f4. but we may or may not get that. We might actually get an output x hat that belongs to this summation, which is a weighted sum of just F1 and F3, meaning F4 got the weight of 0, even though F4 is agent 4 is a good agent, and F2, the function of agent 0 who is bad, also gets the weight of 0, which is desirable. In general, the weights assigned to these weights that we end up with, even though we cannot compute them explicitly, that weight distribution will depend on the cost functions themselves, meaning the cost functions of the good agents, F1, F3, F4, and also the behavior of the faulty agents. Something to observe in the algorithm that I presented earlier, going back a few slides. Notice that this algorithm makes no attempt to identify the faulty agents. We are not assuming or implying that the gradients of the agents that supplied the T smallest or the T largest gradients are faulty. That may not actually be true. And what we may be throwing away are gradients from good agents, or perhaps gradients from bad agents too. It's just that we just don't know. And the claims about the algorithm do not depend on which agents, which of those agents are faulty and which are fault-free or good. And that's nice because we don't require identification of the agents to achieve the property that we are claiming. Now, in some cases, identification may be possible. And let me give you a very simple example. If I were to ask you for the cost of meeting somewhere, so I'm in Washington, DC, and let's say two of us want to meet for dinner somewhere in the city, and if I were to ask you for your cost function, where the cost is maybe the cab fare to meet at various places in the city, and you provide me a cost function that is 0 where you are and $1 million everywhere else, then I know clearly there's something wrong about this cost function. It should not cost you $1 million to go anywhere in the city by a cab. And if you provide me a cost function or the gradients of a cost function that are obviously wrong, then the server in this case can actually identify the faulty agent. But the algorithms we're going to discuss will not try to identify the faulty agent. To put it differently, we're going to assume that the adversary is smart enough to not supply information that is detectably bad. In other words, the adversary will behave as badly as possible without being detected as faulty. And or at least that's the attempt that the adversary is going to make. And therefore, the algorithms we design will not even attempt to diagnose anything. They'll just try to somehow mitigate the impact of the faulty nodes. Okay, so let's move on to functions with redundancy now. Now, I should point out that the algorithm, the filter that I presented earlier, can be applied when functions are redundancy too, and we will talk about it later. But the results I stated about the number of good agents that have 0 weight and so on, those results apply for the setting when the functions have no redundancy. When the functions have redundancy, the same algorithm will behave much better, as we will discuss later in the tutorial. So now let's talk about functions with redundancy. Like I said, there are 2 versions of these problems that we'll discuss, the so-called exact redundancy or exact resilience and approximate resilience. We'll start with the case of exact resilience. So the goal of exact resilience is to in fact solve the problem that we set out to solve exactly, which is to say, I in fact want to compute value, an argument that truly minimizes the summation of the cost of just the good agents. And the example or the counterexample we discussed earlier says that you can't actually do that if the functions are completely independent. So clearly the functions need to have some dependence on each other for us to be able to solve the problem. When there are some bad agents in the system, we're going to assume there are always n agents in the system, of which up to t agents can be faulty or compromised. And the question is, if you want to do that, what properties do the functions need to have? This goal is what we're going to call T resilience. Tolerating T false is what we're going to call T resilience. So before I state the condition under which T resilience is possible, let's take a trivial example in which T resilience is in fact possible. So remember that we have all these different agents, 1, 3, 1, 2, 3, 4. Let's say 4 is the bad guy, but 1, 2, and 3 are actually good. What if all these agents have the exact same cost function? Right? So let's say you're going for dinner somewhere, and we are all in the same conference room right now, and we're all going to go to dinner. And of course, the cost, we are starting from the same place, going to the same place at the same time. The cost functions are going to be identical. So the problem is actually quite trivial because everybody has the same cost function. In particular, the argument that minimizes the summation of the cost function over all the good agents is identical to the argument that minimizes the cost of any one agent. So if I am agent J, all I had to do is just compute my own minimum and argument that the X then minimizes my own cost function and go there for dinner. And I know you will show up in the same place too because you have the same cost function. So it's sort of trivially solvable. Of course, in the server-based setting, you need one more step here. So this is the algorithm for the server. The server now is going to assume this algorithm only works if the cost functions are all in fact identical. Then what the server expects from all the good agents is identical gradients, because if f1 equal to f2, then the gradient of function f1 at xk and the gradient of function f2 at xk is identical as well. So all that the server will do then is to get those n gradients and take a majority vote across the n agents. If any f plus any t plus gradients match, then those are that gradient value is the true value, and you would use that here. So that's all is the algorithm. And as long as majority of the agents in the system are non-faulty or well-behaved, this algorithm will give you a correct outcome. So it's sort of a trivial example, but it makes the point that indeed there is a way to solve the problem we want to solve exactly, right? We can in fact achieve this goal of T-resilience exactly, provided that the functions have enough redundancy. And the redundancy I took was rather extreme. Essentially, it's full replication. Every agent has the same information. They all have the same cost function. If it is machine learning setting, then it would mean that all the agents have the same data, or every agent is producing data items from the same distribution, right? They're all identical. We will come back to this setting later on, even though it's so extreme in that all the agents are actually treated as essentially equal or identical. That's the setting that is very commonly assumed in the work on fault-tolerant learning. Right? This tutorial is about fault-tolerant optimization and learning. Learning is a special example, special application of optimization, but in particular in stochastic learning, most of the literature on fault-tolerant stochastic learning assumes that all the agents are actually identical. And as I showed on the previous slide, the problem is quite trivial because you can solve it by just majority vote on the gradients. And what makes stochastic learning non-trivial is that because the gradients are stochastic, even though they're identical in expectation, right, the average or the expected value of the gradients are identical for all the agents, the actual stochastic gradients supplied by the different agents are not necessarily identical. So we cannot just use a majority vote on the gradients as a way of filtering out the bad behavior. And that makes the problem non-trivial, even if the agents are all identical. In particularly, stochastic gradients is what makes this interesting. And we will talk about that actually in part 4 of the tutorial, not today. But for now, I'm focusing not on stochastic gradients, but the case where what I'm going to discuss today are deterministic algorithms, meaning the agents are supplying the true gradient of their cost functions, not the stochastic gradient. And this is the claim that T-resilience means that we want to compute the argument that minimizes the cost over cost of the aggregate cost of all the good agents. That's what I want to compute, all the good agents, right? Not just n minus, not just some of them. You can actually achieve the goal so long as the cost function satisfies this property called 2T redundancy. And I have not defined what this is, so let's define what 2T redundancy means. And this is if and only if, so it goes both ways. So what is 2T redundancy? It says that if there are n agents of which up to t may be faulty, then 2T redundancy is this property. It says that the arguments that minimize the aggregate of any n minus 2t cost functions of good agents, or any n minus 2t non-faulty cost function. Those arguments, the set of those arguments is identical to the arguments that minimize the aggregate over all the good agents. Right? So it's a very strong requirement. It says that if what I really want is an output x hat that's in this set, the argument that I want to compute x hat that minimizes the aggregate over all the non-faulty cost functions, or the x hat is the argument that minimizes the aggregate of cost function of all the good agents. That's what I want to compute. But for me to be able to compute that, this set and this set has to be equal. Right? So in other words, it suffices to compute the argument of any n minus 2t non-faulty agents to compute or output x hat correctly. Of course, the trick is that we don't know which agents are faulty or which agents are good. So you want to compute that x hat correctly without being able to identify the faulty agents, or without explicitly identifying the faulty agents. So this slide just states the same property slightly more formally. If S is a set of all non-faulty agents and T is the set of any n minus 2t non-faulty agents, then the 2t redundancy property requires that the argmin of sigma fi, where I belongs to S, is equal to argmin of sigma fi, where I belongs to T. Right? And this is the same thing as what I said earlier on the previous slide. So this property is necessary, meaning if you don't have this property, then you cannot solve the problem correctly. And it's sufficient. There exists at least one algorithm that solves the algorithm that gives you desired output if this property is satisfied. And the question, of course, is this property realistically achievable in practice? In some settings it is. And I will talk about some settings where maybe you cannot achieve it exactly, but you can approximate it. And in fact, that's what we mean by approximate resilience that we'll talk about later on. So here is an example where this property may be exactly achievable. So you may have seen this story before, where you have an object, in this case, an elephant, and there are many observers, and maybe a single observer cannot really decide what object they're looking at. But if many of these observers collaborate, then they can figure out the object that they're looking at. And if you have n equal to 6, in this example, 6 agents, and of which one is faulty, then this 2t redundancy property that we are demanding basically says that any 4 agents that are well behaved, right, any 4 good agents should be able to correctly identify what object they're looking at. If the information available to any 4 agents is sufficient to determine the object correctly, then I have 2t redundancy in this case. Y4, n equal to 6, t equal to 1, n minus 2t is 4. And so intuitively, this property is essentially saying, for this particular example, is saying that any 4 of the 6 agents that are well behaved should be able to correctly solve the problem. Of course, the difficulty is that me, as one of the agents, don't actually know who else is behaving correctly. But if I knew, then any 4 of us can together solve the problem correctly. So it could be those 4 or this 4, as long as they are behaving correctly. So we saw this problem of linear regression previously, wherein we have available y and a. Y is a column vector, A is a matrix, and the goal is to compute x star such that y equal to ax. And so long as matrix A has the right properties, then there is a unique solution for y equal to ax. In particular, of course, matrix A needs to have the adequate number of rows, but also it should be full rank, so that there is a unique solution to this problem. And in the distributed setting, this matrix A or vector Y is not known to any single agent, but each agent has partial information, part of the matrix A, and some rows of matrix A, and some elements of vector Y rather, in particular AI and yi at agent I, so that yi equal to ai x star, and we define this cost function fix equal to yi minus ai x square. And we observed that so long as the original problem has a unique solution x star, then the argmin of the summation of the cost function over all the agent is also unique and equal to x star. And so one way to solve the original problem is to solve this optimization problem and compute x star as a solution of this particular problem. Now, if you have false, then we don't want to compute the argmin for the summation over all the cost functions because some of them may come from faulty agents. And so you really want to compute the argmin over just the non-faulty agents. In other words, what we need is that if you take the rows of the matrix A known to just the non-faulty agents and solve the problem using just that submatrix, then it should have the unique solution X star. So at a minimum, if you knew all the non-faulty agents, then they should be able to solve the problem correctly, given that, provided that we knew who the non-faulty agents are, all of them. And that's what X star over here, X star equal to argmin summation I belongs to S, fi of X means. It just says that if S is a set of all non-faulty agents, then collectively they can compute X star correctly if they knew who the other non-faulty agents are. But a 2T redundancy condition will require that not only do I need X star to be equal to the solution of the optimization problem over all the agents, but in particular, we need the argmin for the aggregate cost function over all the good agents to be equal to argmin over argmin for the aggregate cost function of any n minus 2T agents. And that's the condition we saw earlier for 2T redundancy. If that condition is true, then we know that we can have T resilience. In particular, we can compute X star. But what does that those two argmins being equal mean? It basically means that if you take the rows of matrix A corresponding to any n minus 2T agents and form that submatrix and take the corresponding values in the y vector, then that subproblem has a unique solution, which is also equal to X star. And so in effect, what we need is enough rows in this matrix, and in particular, the rows corresponding to any set of n minus 2T non-faulty agents should be enough to solve the problem correctly and compute X star uniquely. And if we have that, then we have 2T redundancy, and then we can use the optimization for framework or fault-tolerant optimization framework and also solve for X star. The point of this two example was simply to show that it is in fact possible to imagine situations where the 2T redundancy property is in fact satisfied. If it is satisfied, then here is a very simple algorithm that allows you to achieve the T resilience property. It's a centralized algorithm, and then we'll talk about distributed algorithm later in the tutorial. So what does centralized algorithm do? Remember that there are n agents up to T of which may be faulty. There is a server, and this is a very simple algorithm, not necessarily a practical algorithm, but just to make the point that if you have 2T redundancy, then T resilience can be achieved. So what's the algorithm? The agents supply their entire cost function to the server. So if I am agent 1, I describe my cost function f1 of x to the server. Agent 2 will describe cost function f2 of x to the server, and so on. Now, the faulty agents can send to the server whatever cost function they want. They can just make one up. It can be a bogus cost function. And here is what the server does. Server has now n cost functions from the n agents, of which T may be bad ones, like bogus functions. So the server's goal is to find a set S of size n minus T, right? A server S containing n minus T agents, right? All but T agents. And this is the argmin of the summation of cost functions over that set S. And then I'm going to check for every subset T, right? Subset of set S, where T has size n minus 2 little t, 2 times the number of faults that we want to tolerate. I'm going to check that this equality is satisfied. Okay, so let me start again. I pick one particular set of size n minus t and compute the arguments, that the set of arguments that minimizes summation fi of x, where I belongs to set S, right? That's the left-hand side here. And then compute the set of arguments, the arguments that minimizes the cost on the right-hand side, corresponding to set T of agents. That's a subset of S of size n minus 2t. And I check this for every such subset. If it happens to be equality for all the subsets, then I will output an x hat in this set. On the other hand, this equality is not true for even one of these sets T, then that S is not the good one. I throw that out, try a different S, right? There are many such choices for set S. I'm going to just go through them exhaustively until I find one of them. And if the functions satisfy 2T redundancy, then such a set S necessarily exists. And we will output X hat that's in fact correct, meaning it's in fact an argument that minimizes the cost, the aggregate cost over all the good agents. Okay. And the proof of that is actually not that difficult at all, but I will not discuss the proof here in my tutorial. Okay, so this simple algorithm is an existence proof that given 2T redundancy, T resilience is actually achievable. And in fact, 2T redundancy is necessary and sufficient to achieve T resilience. So even though the property may seem very strong, it's unavoidable if you want to achieve this outcome of T resilience. So of course, we can compromise on the outcome, meaning we can say, okay, maybe when my functions don't satisfy 2D redundancy, I cannot achieve T resilience, and maybe I'll do something weaker. And that's what we're going to talk about actually next part now. So this is something I discussed just now. So that's the claim, right? I already said this, that 2T redundancy is necessary and sufficient for T resilience. The distributed algorithm for this actually is quite simple. It's very similar to the picture I showed you earlier, right? With the server and the agents and the filter gradient. The only question is, what's the filter? And later in the tutorial, once I've introduced a number of different filters, I will point out a couple of filters that actually provably solve the problem. In fact, it's quite possible that many of the other filters that I'm going to present will also solve the problem, as long as there is 2T redundancy, along with some additional properties. And depending on which filter you use, those additional constraints may actually change. But I'm going to defer the discussion of the rest of the fault-tolerant algorithms, as well as approximate resilience, which is the next topic, to part number 4 of the tutorial. Okay, so what did we do today? We introduced the problem of fault-tolerant optimization and learning. We looked at the case of independent functions, essentially functions with no redundancy, pointed out that this particular problem, as specified here, is not solvable because we are focusing on the sum of just the good cost functions. We cannot solve the problem when the functions are independent or have no redundancy, but we can approximate it. And the approximation that we showed for independent functions was to have a non-uniform weight distribution instead of a uniform weight distribution. And the simple solution I presented for the scalar case, in fact, comes pretty close to the best possible weight distribution you can have for the scalar case. Then we talked about the notion of redundancy, in particular 2T redundancy, and showed that it achieves what I call exact resilience. And next time, we will begin here. We will talk about the notion of approximate resilience, and I'll introduce a necessary and sufficient condition for that as well. And then I will take examples of many more filters for these gradients that actually let you achieve, let you solve the fault or optimization problem with various desirable properties. So with that, let's stop with part number 3 here.